welcome to CEC lectures. In our series of this operating system concepts, in the previous lectures, we have seen the process management module, and presently within the process management module we have seen the job schedulers in the previous lecture. Now we will drill down more into the job schedulers and the process creation and the operations of processes. So we till this point we have seen our long term scheduler and the short term scheduler, and we have also studied the frequency of execution of this long term scheduler and short term scheduler. But this is not only the scene between long term scheduler and the short term scheduler. One more intermediate level of scheduling is there in some of the operating systems such as time sharing systems, because in the previous lecture I have told you that in some time sharing systems like Microsoft Windows and Unix, there is no long term scheduler. It is the job is just taken up and loaded into the memory, and the short term scheduler is going to take care of that particular job. So these systems may have an additional, so please notice, may have an additional intermediate level of scheduling, which is known as the medium term scheduler. Now why this medium term scheduler is required? So sometimes it is very important to remove a process from memory, because it is we can say generating a contention for the CPU, and thus we need to reduce the degree of multiprogramming. Now, but later this process can be reintroduced into the memory, and its execution can be continued where it is left off. So basically what I can say here is your CPU is executing some process. That process has to be kind of taken out from the CPU execution, can be put up again into the memory after some time. So once it is taken out from the CPU, and then it is going to be stored somewhere else, and maybe later off it can be reintroduced into the memory, and then it can continue its execution from the particular point where it has left off. So this scheme is basically known as swapping. So basically a process is swapped out and then swapped inside the system, and the job of swapping is being handled by medium term scheduler. So sometimes this swapping is necessary to improve the process mix. Now what kind of process mix I am talking about is the processes which are having CPU bound processing or the input output bound processes also. So as we have seen in the previous lecture that to make a system balanced, there has to be a proper process mix. So sometimes this activity of swapping will help a lot in improving the process mix, because in this swapping what is being done, so memory commitment sometimes has been over committed, then kind of this some memory has to be we can say released, some memory has to be deallocated, and this can only be done with the help of medium term scheduler. So in order to have a feel of this medium term scheduler, let us try to explore the figure which is given on the screen. So we have one a ready queue. This process is coming inside the ready queue, it will take on to the CPU, and then because of some reason this the process which is holding the CPU is taken out, or more technically we can say it is swapped out, and it is kept in the area where the partially executed swapped out processes are being kept, and then maybe later on it is again swapped in, kept into the ready queue, and then we have here it for CPU in the next maybe in some next moment of time. So this is what the concept of your medium term scheduler is. So some systems which are not having long term scheduler may have medium term scheduler as well. Now coming to the concept of context switch. The context switch is a very important concept when we talk about the process management module. Now, what is this context switch? Let's see. So, we have talked about interrupts. These interrupts may cause the operating system to change a CPU from its current task and to run a kernel routine. There is an kind of an interrupt which is interrupting the CPU, taking its current task from its hands and keeping it somewhere aside, and it forces the CPU to run a specific kernel routine. So, whenever this interrupt is occurring and CPU is releasing a particular process, the context of that CPU which was running on the which was running currently has to be saved completely. Now, what kind of context I am talking about? So, the context basically, first of all, it is stored inside the PCB. PCB is process control block. This also we have seen in the previous lectures, that the value of CPU registers, what is the state of the process, what is the related memory management information. All this information makes a complete context. So, whenever process is taken out from the CPU, whole of its context is to be saved, because later that process has to resume from that particular point only where it has left off. So, this context is represented, or we can say this context is stored inside the PCB, and then this context will be restored when this processing is done, and essentially suspending the process and then resuming it requires this context switching. So, basically what has happened, that state save of the current state of the CPU has taken place, whatever mode it is in, whether it is in the user mode or whether it is in the kernel mode, and then state restore is also required to resume the operation from there where they have left off. So, this particular process of switching taking the process from the CPU, is storing its complete context, and then again taking the context and resuming the processing. This is known as context switch, and it is a very important concept. When we will in the upcoming lectures, we will go through the speed and all those kinds of things. Then we need to come back to this context switch. Now, apart from this context switch, we also need to go through the what kind of operations are there which are performed by the process. So, is it just only kind of an execution which a process is doing on a continuous basis, that is kind of it is whether it is it just the processing? So, I can say no. The processes in most of the system can execute concurrently. Also, they may be created and deleted dynamically. So, basically it is not only the execution of process, but it is also systems must provide a mechanism for process creation, process termination, process execution is also of course there. So, process creation is going to, as the name indicates, it is going to create several new processes. So, several new processes which are created are known as child process, and then the process which has created these child processes are known as parent processes. So, this is a simple hierarchical system. So, for example, in most of the operating system, let us say Unix, Linux and Windows, these processes are identified with the help of a unique number which is known as a process identifier, or this is in short it is also known as a PID. This PID is nothing but an integer number, and this integer number is unique to each and every process. So, this PID provides a unique value for each and every process in the system, and it can be used as an index to access various attributes of a process within the kernel. So basically this process ID is not just the identification number, but it is also going to be kind of, we can say, represent various attributes of the process within the kernel. Now there is a, let's say there is a process which is running, which is going on, the execution is in the is on the run, and meanwhile it creates a child process. So now there are two processes, considering only these two. One is the parent process which is already going on, and the second is the child process which has been just created by this parent process. Now what will happen to this child process? This child process will need certain resources. What kind of certain resources I am talking about? If it has been created, it needs to be loaded inside, somewhere inside memory. It may require some input output devices, or it is also most probably it is going to take some CPU cycles or CPU time also. Then only this child process is going to accomplish its task. So how this child process is going to obtain its resources? So there can be two, I can say, ways from which this child process will be able to get to these resources. So one is directly from the operating system, and another one is from the parent process. So if it obtains the resources directly from its directly from the operating system, that is one scenario. Another scenario is it may have the resources from the constraint pool of the parent process itself. So if it is going to take the resources from the parent process, that means one thing is very, very clear, that the parent process may have to divide its resources among its children. Now it could be one process which is the child process, or it could be many children processes. So basically now the concept comes as the parent process may be able to share some resources among several of its children. Now that is one requirement which is just generated, that there has to be some kind of inter-process, I can say, communication or linking. We will be taking up this also. Now another constraint which comes with the process creation is restricting a child process to a subset of the parent's resources prevent any process from overloading the system by creating too many child processes. Now this is a fact that the system may have created many of the child processes which results in the overloading of the system. Now if there is a restriction on the child process to a subset, there is a restriction on the child process to use a subset of the parent resources, then only this thing can be prevented. Otherwise it is very difficult to prevent the overloading of the system. So why I am telling you all these situations, that these are basically things which are coming with these are the constraints which are they have started generating with the process creation. So process creation is just not a parent process is running and it has created a child process and that's all. No, it is not like that. It has to be kind of various constraints are to be kept into the mind, that how this child process is going to fulfill its need of the resources. Are many of the children processes kind of allowed to be generated? So the answer is no. And as far as resource acquirement or resource allotment is concerned, either it has to be through the operating system or through the parent process. So giving the resources from the parent process is going to have some control on the overloading of the system. So this was about the process creation. So it is not only about the creation, along with the execution and creation, there comes also the concept of process termination. So process termination has to be there. Now, when we talked about process creation, one thing which I would like to add there is this, what will be the command through which the child processes are being, created. So, in Unix and Linux machines, the command is fork. So, fork is going to create the child process. Now, coming to the process termination is, let us say one child process has been already created, and now it has stopped, or it has finished its final statement, and now operating system is supposed to delete this by using a particular system call, and the system call which was fork for the generation of process. Similarly, we have exit system call for the termination of process, and at that point the process may return a status value to its parent process via the wait system call. So, that means once the exit system call will take place, there will be another system call which is known as wait, and this wait is going to return an integer to the parent process, and the significance of that integer is this integer is going to be kind of an indication of the status value. That means, let us say for example, if it is integer x, that means the process has been we can say successfully terminated. If it is exit y, it could be an error or something of that sort. So, the status value and the wait system call through which this status value is being returned to the parent process are important as far as termination is concerned. Not only the error or the successful execution, a parent may terminate the execution of one of its children process for a variety of reasons. There could be many reasons. For example, a child process has exited its usage of some of the resources that it has been allocated. Some resources has been allocated to a child process, and the process has exceeded the usage. Then it is kind of become a hungry process, and it is taking up the more resources. So, then in that situation also a parent process may want to terminate the execution of that particular child process, or we can say another situation could be a task which is assigned to the child process is no longer required. There is no need of that particular task to be completed. Or another idea could be the parent is exiting and the operating system is not allowing a child to continue if the parent is terminating. That means forcefully a child has to be terminated. So, there can be various conditions. So, the condition which says the child has exceeded its usage of resources which were already allotted to it. In order to determine actually what has occurred in the child process, the parent process must have a mechanism to inspect the state of its children, and that can be done through those integer index values which are PIDs, process identifier, these index values which are given to the parent process through the wait system call. No, not the parent ID, sorry for that. So, the task assigned to the children is no longer required, child process has become more hungry, or the parent is coming out and it is not allowed by the operating system to continue its children to go there, children to continue its processing. We can say all these scenarios are something which requires the termination of the process. Now, when we study termination of the process, we also have one term which is known as cascading termination. So, cascading termination comes with the third scenario which we were just discussing, that some systems do not allow a child to exist if the parent has terminated. So, if the parent has terminated, it is mandatory for a child process to get terminated. So, in such system, if a process terminates whether abnormally or normally, then its all children must also be terminated, and this phenomena is known as cascading termination, and it is normally initiated by the operating system because it is the policy of the operating system, or it is operating system as an entity is not allowing the children process to continue if the parent is getting terminated. So, in case of termination of parent, if the children are also forced to terminate, this phenomena refers to as cascading termination and is generally in normal situations it is initiated by the operating system. Now, we have seen that apart from this process execution, there are scenarios of process creation and there are also the scenarios of, I can say, process termination. And what is this creation, how through which system call it is going to happen, in what scenarios it is going to happen and how it will be handled. That we have seen that the creation of child process, why those child processes are created, who is going to allocate them resources, through which whatever the ways through which these resources are being allocated, why those ways have been opted for, all these we have seen in process creation. Then in process termination we have seen why a process need to terminates, whether normally or abnormally, and then we have also seen the cascading termination as a term. Now, this is a very clear scenario that in this whole picture we also need some processes to communicate with each other. For example, a parent needs to communicate to a child, or maybe a child 1 needs to communicate to child 2. So, there has to be a kind of, we can say, communication which is happening between the processes, and this is known as inter-process communication. Now, why this inter-process communication is being taken place, or what are the advantages behind this inter-process communication? Let us try to explore. So, we have many resources. For example, we have many resources which are to be shared. For example, we have a file which is to be shared among many of the processes. So, that means several users are interested in the same piece of information. That means that file has to be kind of, we can say, shared between many of the users. And now it is a very common scenario with huge systems of bankings and railways all around us. We have shared files which are simultaneously used by many of the users. So, basically concurrent access to information or to a particular piece of information, concurrent access is required. So, the system has to have an environment to allow the concurrent access to such information. So, that is the first, I can say, need or the advantage of inter-process communication, that information sharing wherever required is going to take place with the help of your inter-process communication thing. Now, it is not only the communication, it is also the computation speed up. Computation is speed up, that means if we want a particular task to run faster, then we generally do that we break it into the subtask and all the subtasks are going on in parallel. Now, imagine that there is a kind of big program which is broken up into various modules, and all these modules are executing in parallel. Then let us say there is a variable which is going to be used by many of these modules. Then that variable, in the language of programming, we say it as a global variable. So, these kinds of global variables are the data which are required by all the subtasks. And the reason here of dividing this the problem into subtask is we want to speed up the communication, speed up the computation. So, this speed up can be achieved if the computer has multiple processing cores, and in case of multiple processing cores, there has to be an area of the information, or there has to be some information which is going to be shared. So again here inter-process communication is required. Not only this, but then we go with another concept which is kind of parallel to this, is modularity. We want our system to construct in a modular fashion, because dividing the whole system into various functions, maybe into separate processes, or we have also seen the concept of threads. So dividing the system functions into separate processes or separate threads helps in achieving the modularity, we can say. So inter-process communication is required for information sharing. It is also required for computation speed up. It is also required to achieve modularity, and modularity has its own benefits. Not only these three, it is also required to achieve convenience. So how can we say that convenience? So for example, an individual user may work on many tasks at the same time. For example, it is kind of editing a document, it is something is kind of getting compiled in parallel, a printer process is taking up the resources of the printer and getting printed, and the user is also listening to music. So that means from the point of view of operating system, if you can see that yes, definitely there will be some area or some information which is required by all these instances of editing, compilation, printing and listening to the music, because all these processes are taking up on a single system, in a single system by a single and individual user, which is doing some multitasking thing. So convenience, modularity, computation speed up and information sharing also are the kind of, we can say, key advantages or the needs behind ensuring inter-process communication. So let me summarize this lecture. In this lecture we have seen the process creation thing, we have also gone through the process termination, and apart from process creation and process termination and all its nuances we have seen, and also we have seen what is the need of inter-process communication, and inter-process communication in detail we will be taking up in the upcoming lectures. So hope you had a fruitful learning. Here is a list of references which is being used for the preparation of the lecture. Thank you for a patient hearing. I will see you soon in the next lecture.